Hello everyone, welcome to Unit 2, Part 1. This particular unit is going to be discussing the issue of apportionment. You might recall back in Unit 1 we were talking about the different voting methods, weighted voting methods, and issues surrounding those voting methods, and we kind of capped off the unit with a lengthy discussion about the Electoral College. And one of the questions that I had asked you to complete in there was to tell me about the Electoral College, and a lot of you guys commented about how there was a certain number of electoral votes that were given to each state based on their population. All right, so how did we determine the number of electoral votes that each state gets? And that is actually done through a process called apportionment, and it's the idea of dividing up a fixed number of things based on population. All right. So the way that we determine how many electoral votes that California gets, or Illinois gets, or Texas gets, or Alaska gets is based on the population of that state. And the issue of apportionment is extremely important because we actually use apportionment to determine the number of representatives in the House of Representatives in Congress, which directly affects how many electoral votes we get for each state when it comes to the presidential election. So this is a very important piece of math that determines a lot of things within our government. All right, so this is probably one of the most relevant pieces of math coming up here in about a month, and you'll really have an in-depth understanding that most people don't about where the electoral votes come from, how they're used, and how we end up in this complex weighted voting / plurality system of selecting a president that we use. All right. So let's get to it. There's a couple of rules when it comes to apportionment that we need to make sure that we observe. We need to make sure that when we divide things up, we can only exist in whole numbers, right? So the things being divided up can only exist in whole numbers. So in other words, you can't have half of an electoral vote. You have to have one electoral vote or two electoral votes. You can't have 1.5, okay? We have to use all of the things being divided up. We can't use any more, and we can't use any less. Right? So if we're going to apportion 100 seats, we have to use all 100 seats in the House of Representatives. Okay, so we can't have any leftovers. All right, and the number of things assigned to each group should be approximately proportional to the population of the group. Our goal is to divide things up or disperse things based on population the best that we can. All right. Now, let's kind of move forward here. This is kind of a explanation about how the House of Representatives and how the rules kind of apply to the apportionment for the United States House of Representatives. All right, and it's just what I explained. Right. Now, the first person to come up with an apportionment method in the early years of our country was a guy named Alexander Hamilton, and you might know him. He was one of our founding fathers, and his method was approved in 1791 in Congress, but it was eventually vetoed by President Washington. He did not like the method, and we'll talk about why that is later. Now, his method made a comeback in 1852, surprisingly, and it was used all the way up through 1911. And we'll see why it was discontinued in 1911 as well. All right, it does have some issues. So here are the steps. This is what Hamilton proposed. All right, so he wanted to determine how many people each representative should represent. And the way that we do this is simply by taking the total population of all the states and divide by the total number of representatives that we're apportioning. Right? So if we, as a Congress or as a country, decide to have 100 representatives, then we need to apportion those representatives based on the total population, right? So each representative should represent 100,000 people or 200,000 people, and we want to try and keep that the same throughout each state. All right. So then his next step was to divide the state's population by the divisor to determine how many representatives it should have. All right, and this yields a number called the quota. Now I'm only going to read the first two steps to you here, and that is because these first two numbers, the divisor that we're finding and the quota that we're finding, are going to be the same for almost every method of apportionment that we talk about. So these are the two most important numbers that are going to be discussed in this example. Okay, so I'm going to let you read through the rest here, and then I'm just going to demonstrate these. I think it's a lot easier to demonstrate than it is to try and explain it. So let's take a look. So here we go. So we're going to start with a smaller example. So we're going to look at the state of Delaware, and the state of Delaware has 3 counties: Kent, Newcastle, and Sussex. The Delaware State House of Representatives has 41 members, right? So they're telling us that we're going to be apportioning 41 seats between these 3 counties, all right? Now, if Delaware wants to divide this representation along county lines, which is not required, but let's pretend that they do, we're going to use Hamilton's method to apportion them. All right. Now the populations of the counties are as followed, and this is from the 2010 census. Right, so we have 162,310 in Kent, 538,479 in Newcastle, and 197,145 in Sussex. So when I add those populations up, I get a total population, and we're going to divide by the number of representatives we're trying to apportion. Okay, so when I divide those two numbers, we get 21,900.82927. I don't know why my decimal points are disappearing here. Weird. Okay, so there we go. So what this is trying to tell us is that each representative, each one of these 41 representatives, should represent about 21,900-ish people. All right, so let's move on to step 2, according to Hamilton. So the next thing we want to find are these things called quotas. All right, so these quotas are essentially a number that tells us how many representatives each county should get approximately. All right, and the way that we do that is we take the population and we divide it by our divisor that we found up here. So we're going to take 162,310 and we're going to divide by 21,900.82927. Right, and I carried a lot of decimal places because we want to be as accurate as possible on that decimal place, and you'll see why later on. I know I kind of ran over into the quota column here, but our quota, if we do this division, is going to be 7.411. Okay, and what that's telling us is that Kent should get 7-ish representatives. Okay, and then we're going to take Newcastle and we're going to divide by 21,900.82927, and we get 24.587-ish representatives for Newcastle. Okay. And then we're going to go to Sussex and do the same thing. So 21,900.82927, and when we divide those two, we get 9.0017, right? So 9-ish representatives for Sussex. Okay, so that's the divisor. These are the quotas. You will essentially start with these first 2 steps in every method of apportionment that I show you throughout this unit. All right, so let's go to the next step according to Hamilton. Okay, so what Hamilton proposed, right, to get what we call the initial apportionment was to ignore the decimal parts. Right, so we're going to take these decimal parts and we're going to ignore them. They are now gone. And then we would initially apportion 7 representatives to Kent County, 24 to Newcastle, and 9 to Sussex. And if I were to add those up, we would get a grand total of 40 representatives. Now remember, our rule said we have to use all of the representatives. Well, I've only apportioned 40 and we need 41. So that means there's 1 remaining representative. Now how do we decide who gets that extra representative? Well, what Hamilton proposed was, now let's ignore the whole number part. So we're going to ignore these, and whoever has the highest decimal portion after the whole number gets the extra representative. So if we look here, Newcastle has the largest decimal portion at 5872. So this 24 in the final apportionment is going to turn into a 25. The other two counties will stay the same. And now when I add those up, I have 41 representatives. So that was Hamilton's proposed method of apportioning our representatives throughout Congress and throughout all the states, right? So, and that's a quick example with Delaware's Congress. All right, now it seems pretty easy. It is very straightforward. It doesn't seem like there's a lot of complex math, and it seemed like it was fair. Now, as you know, with any voting method, with any apportionment method, there are going to be issues, all right? And we will talk about those issues later on. We're going to talk about why George Washington didn't like that. We're going to talk about why it was discontinued in 1911. All right, but let's do one more example. We'll run through this one a little bit quicker just to make sure that you got this process nailed down. All right, so we're going to skip over to Rhode Island this time. Rhode Island has 75 seats in their House of Representatives, and it has 5 counties with the populations listed here for us. All right, now I totaled them up for you, and we're going to calculate the divisor in step 1 here. So we're going to take that total population, we're going to divide by 75, the number of seats, and what we find for Rhode Island is that we get 14,034.2267. All right, so that means every representative should represent about 14,034 people. All right, and we're going to try and stay as close to that as we possibly can using Hamilton's method. Now, the next thing we need to do is we need to determine quotas. All right, so the way that we determine quotas is we take county population and we divide it by the divisor. Right. So I'm not going to write out each division like I did in the last example, but we're going to be doing this for each of the 5 counties here, and then we'll write the results. So here we go. Feel free to check my numbers. All right, so there we go. Those are the numbers that I got. Like I said, feel free to check them. If you did the divisions yourself and they're slightly different, send me an email. That way I can make a note of that for other people. So now what we're going to do is Hamilton's next method, which is to remove the decimal part from each quota. So I like to pretend I'm taking a box here. I'm cutting off all the decimal portions. It's important to remember we're not rounding. We're not considering these decimal portions at all in this step. It's like they don't exist. So initially, Bristol is going to get 3 representatives. Kent will get 11. Newport will get 5. Providence will get 44. And Washington will get 9. And when I add those up, I'll get 72 representatives apportioned. Now we have 3 left over because we have to apportion 75, so we have to determine who gets the 3 extra, or what I like to call the bonus representatives after the initial apportionment. And according to Hamilton, the way that we do that is we take the whole number parts of these quotas and we ignore them. They no longer exist, and we use the decimal portions to determine who gets a bonus representative. So the highest decimal portion is Newport with 0.9061, so their 5 is going to a 6. All right, the next one here is Kent at 0.8395, so their 11 is going to a 12. And the next highest one is Providence at 6528, and they are going to a 45. Because remember, I had 3 bonuses, so I had to find the top 3. The other ones are going to stay the same, so Bristol is going to stay at 3. Washington stays at 9, and now when I add those up, I get 75 representatives. Okay, so like I said, Hamilton, quick, easy, seems fair, and I stress that word, it seems fair. Okay, but we'll find out later why it's not. All right. Another thing to note here, I'm just going to talk about this real quick, is that Hamilton's method obeys something called the quota rule. All right, and the easy way to understand the quota rule says that when we give away those bonus representatives, we should be giving away only one bonus representative to each county. We should never be giving two to any county. All right, so in other words, the difference between the initial apportionment and the final apportionment should never be greater than 1. Right, so Kent went from 11 to 12. They should never go from 11 to 13. And Hamilton's method is nice because it will never do that. All right, it'll always obey the quota rule. All right, guys, that's it for today. Give the practice problems a try and make sure you got the Hamilton method nailed down. If you got questions, make sure you ask in the Zoom chat. Have a great day.